Space is filled with massive, dark molecular clouds, vast expanses of gas and dust that look like nothing more than cold, empty voids. Despite the stars around them, these nebulae can remain dark and frigid for eons. Inside these clouds, two invisible forces are locked in a struggle. There is the thermal pressure of gas particles pushing outward, and the relentless pull of gravity trying to drag everything towards the center. In this state, the cloud is in a stalemate. The outward push of the gas exactly matches the inward pull of gravity, keeping the structure stable and frozen for millions of years. As long as this balance holds, the cloud remains an inert graveyard of raw materials. To create a star, an external force must step in to break the peace. That disruption usually arrives as a shockwave. It might be the debris from a nearby supernova, or the tidal forces of two galaxies passing through one another. When this shockwave hits the nebula, it physically compresses the leading edge. Particles are shoved into a much smaller, denser space. This increased density changes the math. Gravitational pull between the now crowded particles spikes, quickly overpowering the outward push of thermal pressure. The equilibrium that held for millions of years is gone. The cloud begins an unstoppable, accelerating collapse. What follows is a massive freefall. Trillions of tons of gas and dust plunge toward a single central point, picking up speed as density increases. Because the original cloud had a slight slow rotation, the laws of angular momentum take over. As the cloud shrinks, it begins to spin faster and faster. This rapid rotation forces the once spherical cloud to flatten out. Centrifugal force pushes against the collapse at the equator, while poles fall inward unimpeded. This flattened disk acts as a funnel, relentlessly feeding matter down into an incredibly dense central core. At this very stage, gravity has won. It is successfully stockpiling the raw fuel needed to build a star. This central mass is now a protostar. It is a massive, glowing ball of crushed gas, but hasn't become a star quite yet. As gravity continues to pile on more mass, the weight becomes staggering. This pressure drives the temperature at the core to extreme levels. Hydrogen atoms are being shoved together with incredible violence. Normally, these atoms just repel each other, but the crushing weight of the star is beginning to overcome that resistance. For the atoms to touch, the temperature has to reach a specific tipping point. This chart shows the climb toward 15 million degrees Celsius, the point where hydrogen atoms are moving fast enough to collide. At 15 million degrees, nuclear fusion begins. Hydrogen atoms smash together and fuse into helium, releasing a massive burst of energy in the process. This ignition creates an immediate outward pressure. For the first time since the collapse began, the momentum of gravity is being pushed back from the inside out. The moment of ignition sends a wave of energy through the system, clearing away the remaining dust and gas and revealing the new star. The core is now a sustained nuclear reaction. This constant release of energy generates a colossal outward thermal pressure. This creates a state called hydrostatic equilibrium. The outward push of the nuclear fusion now perfectly matches the inward crush of gravity. This balance is what stabilizes the star. Gravity provides the pressure to keep the fusion going, and fusion provides the energy to keep the star from collapsing. This marks the start of the star's longest, most stable phase. Every star you see in the night sky is maintained by this specific balance. They look peaceful, but they are defined by two massive opposing forces, holding each other in check. The birth of a star is the transition from a cold, drifting cloud to a sustained balance of power. This internal struggle acts as the galaxy's forge, producing the light, heat, and elements that make everything else possible.